In this video, we're going to talk about L'Hopital's rule and indeterminate forms. Um, so let's go ahead and get started. This section number this is actually going to be from 5.6 in the Larson Edwards book. And it's going to finish up our discussion on limits and derivatives, even though some of what we're going to get into, lots of times you won't talk about this until the beginning of Calculus 2. We're going to talk about it now at the end of our discussion on limits and derivatives, just to put a nice bow on things. So our objectives today, let's define the indeterminate forms of limit 0 over 0 and infinity over infinity. 0 to the infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, and infinity to the 0. We're going to evaluate limits involving the basic indeterminate forms of 0 to 0 and infinity to the infinity. We're going to use L'Hopital's rule here. And we're going to evaluate limits involving the indeterminate forms of 0 to the infinity by algebraic manipulation, and 1 to the infinity by taking the natural log. So let's go ahead and get started. Our motivating example, let's go back and remember the special trig limit that we had early on. Limit as x goes to 0 of sine of x over x is equal to 1, and we were just told to memorize it, and we said we'd come back later and we'd talk about how we knew that. We're going to talk about that today. We're going to show you how we know that with L'Hopital's rule. So if you tried direct substitution, you'd get nowhere here, that you'd get 0 over 0, which is one of our indeterminate forms. From now on, in the notes, if I write I period, F period, I mean indeterminate form. So indeterminate forms of limits can take the form of 0 over 0 and infinity over infinity. And when we see those, we're going to use L'Hopital's rule. It's important that this can be plus or minus infinity over plus or minus infinity, any kind of infinity like that. So with this example, limit as x approaches 0 of sine of x over x, we're going to use L'Hopital's rule. And we're going to take the limit as x goes to 0 of the derivative with respect to x of sine x over the derivative with respect to x of x. It's going to be the limit as x goes to 0 of cosine of x over 1, which is going to be 1 because cosine of 0 is 1. So let's look at L'Hopital's rule, the theorem. Again, this is from a different textbook. That's okay. So ignore the theorem number here, but let's just pay attention to the theorem itself. Suppose f and g are differentiable functions on an open interval I containing x equals a, where g prime of x is not equal to 0 for any x. If the limit as x approaches a of f of x equals the limit as x approaches a of g of x equals 0, then limit as x approaches a of f of x over g of x is going to be the same thing as limit as x approaches a of f prime of x over g prime of x, provided that the limit on the right exists or is plus or minus infinity. This limit here exists, they're saying, or can be evaluated to be plus or minus infinity. We don't want something over here that we can't determine. what it is. This will apply to anything that's not only 0 over 0, but also plus or minus infinity over plus or minus infinity indeterminate forms. Let's go ahead and say right now, be careful. You take the derivative of the numerator and denominator separately. Do not use the quotient rule. Can't say that enough. That's one of the reasons why we usually don't talk about this in Calc 1, is because we want you to focus on the quotient rule. We do want you to know that the limit of the quotient is the quotient of the limits back in limit properties. Once you learn the quotient rule, we don't usually show you L'Hopital's rule for a little bit because we don't want you to get confused with it since it involves derivatives, but this is going back to that quotient of the limits back in your limit properties, that when you had the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. It's going back to that type of an idea. We're not doing the quotient rule here for derivatives. All right, looking at this example, we want to evaluate the limits. First, let's try direct substitution. 1 cubed plus 1 squared minus 2 times 1 over 1 minus 1 is going to be 0 over 0, which is an indeterminate form. So we're going to use L'Hopital's rule. We're going to get limit as x goes to 1, 3x squared plus 2x minus 2 over 1. And that's going to be 3 times 1 plus 2 times 1 minus 2 is going to be 3. That's our answer. Now, when we try direct substitution here, we're going to get square root of 9 minus 3 over 0 is 0 over 0 is an indeterminate form. So we're going to use L'Hopital's rule. We're going to get the limit as x goes to 0 of here we get 2 root 9 plus 3x. And then this is going to be 3. It's going to be minus 0 over 1. And that is equal to 3 over 2 root 9 is 1/2. So let's just talk for a second here about suggested procedure before we move on to the next problem. One, given a limit expression, try direct substitution first and always. where you can, as long as the limit isn't going to infinity, verify and indicate the specific indeterminate form. 2, if you can apply L'Hopital's rule, do so. Otherwise, use algebra or other techniques to rewrite in an indeterminate form where L'Hopital's rule can be applied, or to evaluate the limit without the need of L'Hopital's rule. We've learned a lot of those techniques already. So 3, if you cannot direct sub because the limit's going to infinity, then analyze the end behavior. If you cannot direct sub because x is approaching plus or minus infinity, or you are approaching a vertical asymptote, use the graph to help verify the indeterminate form, verify whether you're going to plus or minus infinity, you're going to 0, you're going to something else. And then if you cannot immediately apply L'Hopital's rule, then, like I said, we're going to do some algebra and stuff. We'll come to some examples for that. But this one here, we can't evaluate the function as we're going to infinity, but we can talk about the end behavior that this function here, as I go to the right, I'm going up. So I'm going towards positive infinity. This one, as I go to the right, I'm also going up. So this is going towards infinity over infinity. You can verify that with graphs if you would like to. We're going to take the limit as, let's see, we're going to use L'Hopital's rule here. We're going to use it several times. I'm going to take the limit as x goes to infinity of 12x squared minus 12x over 6x squared minus 10. And this still is going to infinity over infinity. So we're going to use L'Hopital's rule again. Some of you remember a technique we did earlier in Calc 1, and you might be already ahead of me saying, why are we doing all this when we already learned a way to make this happen in 1 or 2 steps? And I'm right there with you, but I just want to show you that L'Hopital's rule will get us there eventually. Now let's see if we could have gotten there another way from our calculus 1 techniques that we knew when we evaluated limits at infinitarity. So let's multiply by x to the negative third, top and bottom, and that will give us 4 minus 6x to the negative first plus x to the negative third over 2 minus 10x to the negative second plus 3x to the negative third. And as x goes to infinity, all of these parts with negative exponents go to 0. And that was the same answer, but we just got there a lot more efficiently doing it that way with our calculus 1 technique. So actually, that's exactly what the teacher wanted me to do right here. So let me go back and do that problem again with our calculus 1 technique and show you that we get the same answer. So right here, going to multiply by x to the negative third over x to the negative third. We're going to say that we get limit as x goes to infinity of 4 minus 6x to the negative first plus x to the negative third, 2 minus 10x to the negative second plus 3x to the negative third, 4 minus 0 plus 0 over 2 minus 0 plus 0 is 4 over 2 is 2. No L'Hopital's rule required there. Let's look at another example here. Just make sure I'm not getting too far ahead. Yeah. So additional examples here before this definition that's coming up. So limit as x goes to infinity of 12x squared minus 12x over 6x squared minus 10, which is this one, this piece right here. That's infinity over infinity. We can use L'Hopital's rule. And we're going to get the limit as x goes to infinity, 24x minus 12 over 12x. And then we're going to have to treat that like it's its own problem. That also goes to infinity over infinity, which is an indeterminate form. So we use L'Hopital's rule again. We did all this above, and we got 24 over 12 gave us 2. Same thing. All right. So moving on to this definition, suppose f and g with the limit of f of x as x approaches infinity equals the limit of g of x as x approaches infinity equals infinity. They're both going to some kind of infinity. I just don't know which is growing faster. And I want to look at the limit as x goes to infinity of f of x over the limit as x goes to infinity of g of x, or the limit as x goes to infinity of f of x over g of x is what I'm thinking about here, the ratio of these two functions. So if f of x grows faster than g of x, then the limit's going to go to infinity. If g of x grows faster than f of x, then the limit is going to go to 0. This is just a big concept in math, an important one that we talk about how fast a function is growing, because not all infinities are the same. Some infinities grow faster than others and things like that. So if g of x and f of x grow comparably as x goes to infinity, then like if we had the same degree top and bottom basically, then we're going to go to some constant m that will be our limit. So it's just some things that we know: a higher degree polynomial grows faster than a lower degree polynomial. So like x to the fourth is going to grow faster than x to the third. Right now, e to the x, exponential functions like that grow faster eventually than any polynomial out at their end behavior to the right. They overtake and supersede any polynomial function. Ln of x grows slower than any polynomial function. Most any other function that we know about right now, it's the slowest growing function that we know about, even say the square root of x that grows kind of slowly. Ln of x is going to grow slower and slower and slower as you go out to the right. So the square root of x is going to cross it and stay above it at some point. So evaluate the following limits, and we can just use this big idea here to say that x squared is bigger than x, so we know that this has to go to infinity. So that's our expectation. Let's prove it now with L'Hopital's rule, that if we would evaluate this, we would say that this is going to infinity over infinity, which is an indeterminate form. And we're going to use L'Hopital's rule. Say that this is the limit as x goes to infinity of 2x plus 2 over 1 is going to approach infinity over 1 is infinity. And that's what we expected because the top grows faster. Just say it like this. I won't do it like I did direct substitution. I'll say this is the limit as x goes to infinity, 2x plus 2, which is infinity. All right, moving on to this example here. The top is growing faster or slower than the bottom, so we expect this to go to 0 for our answer. Right now, this is going to infinity over infinity, which is an indeterminate form, so I'm going to use L'Hopital's rule. And this is going to be limit as x approaches infinity, 2x minus 5 over 6x squared minus 2x minus 4, which is still going to go to infinity over infinity. So I'm going to use L'Hopital's rule again. Limit as x goes to infinity of 2 over 12x minus 2. And any constant over infinity is going to go to 0 because k over limit as x approaches infinity of k over x equals 0. Basically what's going on there. All right, now there's other types of indeterminate forms that are going to take, that we're going to talk about here. But actually, let me do one more example here. Example 3, I'm just going to do it in the margin over here. Limit as x goes to infinity, negative e to the x plus 2x over x squared plus 1. This goes to negative infinity over infinity as an indeterminate form. Now, when I use L'Hopital's rule here, the e to the x is not going to go away because remember, derivatives of e to the x keep coming back, right? So I would expect that this top grows faster than the bottom and that I'm going to go to negative infinity, I think, right? So by L'Hopital's rule, this is the limit as x goes to infinity of negative e to the x plus 2 over 2x, which is still going to be a negative infinity over infinity, which is an indeterminate form. And I'm going to use L'Hopital's rule again. limit as x goes to infinity of negative e to the x over 2. Now I'm at a point where I can say this goes to negative infinity, and I can stop, and that is what I expected to have happen. Let's look at another example in this space too. Limit as x goes to 0, x squared plus 1 over negative e to the x plus 2x. So I just basically flipped this over. I already know that the top grows faster than the bottom, so I expect this to go to 0. But this is going to infinity over negative infinity, which is an indeterminate form. I'm going to use L'Hopital's rule. And this is going to be limit as x goes to, this is not 0, this is infinity, of 2x over negative e to the x plus 2 is still going to infinity over negative infinity, which is an indeterminate form. But I'm going to use L'Hopital's rule again. I'm going to get limit as x goes to infinity of 2 over negative e to the x. And that's going to go to 0, just like I expected, because the top is growing slower than the bottom. All right, other indeterminate forms of 0 times infinity and infinity minus infinity. These are going to require algebra. These are going to require logarithmic differentiation. And this is the stuff usually that we like to get to with Calc 2, but I don't mind talking to you about it today. I think you can handle it because we're at our end of our discussion of limits, continuity, and derivatives, and we can just, like I said before, tie all this up together with this discussion here, even though this stuff shows up in like chapter 5. We'll go ahead and talk about it now at the end of chapter 3 before we start our discussion of chapter 4. So let's state the indeterminate forms of the limits below. So this is going towards infinity minus infinity. And this one is going to 0 to the 0. And this one, did I skip one? I did. This one is going to infinity times, and if I stick infinity in here, 1 minus 1 is 0. This one is going towards 1 to the infinity, and this one is going towards infinity to the 0. So those are all different types of indeterminate forms that we can see. Our goal would be to force 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0 into an indeterminate form where L'Hopital's rule can be applied, or where other techniques can be applied and I don't need to use L'Hopital's rule. So indeterminate forms in the type of form up here that are A, that are not 0 over 0 or infinity over infinity, but can easily be manipulated into that form. So first one here, we're going to use algebra, and I'm going to recommend that you multiply by the conjugate here. This is going to give me limit as x goes to infinity of x squared minus x squared minus 3x over x plus root x squared minus 3x is going to give me limit as x goes to infinity of a positive 3x over x plus root x squared minus 3x. Let me get down here to where that is. And then we want to apply L'Hopital's rule if we can. So this is going to be, and I want to just make sure this isn't going to take me around in circles when I do this. So let's try this L'Hopital's rule. It's going to give me limit as x approaches infinity of 3 over 1 plus, and then I've got a 2 root x squared minus 3x there, and I've got a 2x up here, and that gives me I'm just going to try direct substitution now, 3 over 1 plus, and then this is going to be infinity over infinity still. So let's work on that piece separately. Limit as x goes to infinity of x over root x squared minus 3x. I've got the other pieces there taken care of. So let's use L'Hopital's rule. This goes to infinity over infinity, which is an indeterminate form. And let's see, so that's a limit as x goes to infinity of 1 over, and then this is going to be 2 root x squared minus 3x, and this is 2x. And this is going to turn into limit as x goes to infinity root x squared minus 3x over x. And there's no nice way to keep doing this with L'Hopital's rule. That square root part is just going to keep coming back over and over and over again. So we're going to use other techniques that we learned in Calculus 1 already to deal with this. And the way that I'm going to deal with that is, since I'm going to positive infinity, I'm going to write this all under the same square root sign and put the x squared in here with it. And then I'm going to let the limit come inside. And now I'm going to apply L'Hopital's rule. And I'm going to say that this part in here is going towards infinity over infinity. And so I'm going to have my L'Hopital's rule. I'm going to have limit as x goes to infinity of 2x over 2x minus 3. And this is still going, this inside part is still going to infinity over infinity. So I'm still going to apply L'Hopital's rule one more time. And this is going to be the square root of 2 over 2 is the square root of 1 is 1. And I've got that number to come back here and plug in a 1 there. So that's going to be 3 over 2. And that will be my entire limit. So sometimes you see yourself going around in circles like that, and you've got to do some algebra to break the loop. And that's how I recommend that you do that here. There's probably other ways that we could have attacked this problem with L'Hopital's rule to start off with. So let's see what other techniques we could have used. Could have just divided everything by x to start off with. That's basically, that's basically what I did down here. So if we could use a Calculus 1 technique of getting this x out of here and changing this into a situation where we got 0 over 0. That way, we might have eliminated some stuff a little bit faster. Let me show you the other way. Not wrong to do what we did. Let me just show you another another technique. So, because I've got plenty of space here. So limit as x goes to infinity. This is method 2 of original problem was x minus square root of x squared minus 3x. And this is over 1. And let me multiply by 1 over x over 1 over x here early on, like we did earlier in calculus 1. And when I do that, this is going to be x squared minus 3x over x squared here. It's going to be 1 over x is going to be the limit as x goes to infinity of 1 minus, and this is 1 minus 3 over x over 1 over x here. This is going to go to 1 minus 1 over 0 is 0 over 0 is an indeterminate form. Let's try L'Hopital's rule. And that limit will be x goes to infinity of, this comes down here with a 2 in front of it. This is a derivative of what's inside is going to be 3 over x squared is up there. This is a negative 1 over x squared. And yeah, so now I'm going to make this to limit as x goes to infinity of 3 over x squared. And I've got this times a negative x squared over 2 root 1 minus 3 over x, like that. And this is, that goes away. And I'm going to get a should be a positive 3 over 2. Right, this is negative from here. So this is negative, and so that is a positive three over 2 root 1 minus 0 is 3 over 2. And that's the same answer that I got up here. Just a slightly different way of getting to it. All right, let's try another example of a different type of indeterminate form. This one's going to 0 to the 0. So this is going to be part B. So we have a new method that we're going to apply using our log property. That ln of x to the p is equal to p ln of x. So we're going to take the natural log of our limit. At the end, we will have to remember to we will undo this by raising each side, e to the x side. We will undo this. I'll just say, I'll show you how we'll use the exponential function to undo the natural log. So right now we're going to have y equals this limit. We're going to take the ln of both sides. And when we do that, ln of y is going to be the limit symbol can pass through this. The ln can come on the inside. It's mathemagical. It's just a particular type of function that is allowed to do that. And then we're going to examine our graphs. We know 2 to the x goes to infinity. ln of x, as we get close to 0 from the right, is going towards negative infinity. This is going towards 0. So this is 0 times infinity. So we're actually going to take this part down to make it go to infinity. ln of y equals limit x approaches 0 from the right. I can leave the 2 up here. That doesn't matter. I'm going to make this 1 over x. 1 over x as I come at 0 from the right goes to positive infinity. Ln of x, we already said, goes to positive infinity. So this is the indeterminate form of infinity over infinity. We're going to apply L'Hopital's rule on the right-hand side. So that's going to be the limit as x goes to 0 on the right, 2 over x minus 1 over x squared. Going to be limit as x approaches 0 from the right of negative 2x. And that's going to go to 0. So ln of y is equal to 0, making y equal to e to the 0 is equal to 1. So that makes my limit that I was trying to find, limit as x approaches 0 from the right of x to the 2x is equal to 1. Let's go ahead and look at this next one here, where if I try direct substitution, this is 1 to the infinity. Not sure if that's plus or minus, depends which side I'm coming from, but it's 1 to the infinity or 1 to the negative infinity. Figure out what's going on there with this logarithmic differentiation. So x goes to 0, 1 here, like this. ln of y equals ln 1 plus 4x. So ln y equals limit x goes to 0. And I'm just going to say here that this is going to go to, again, some type of infinity times 0. So I'm going to write this way. Now that can be written as 0 over 0, which is an indeterminate form where I can apply L'Hopital's rule. And the constant multiplier just sits there. We differentiate a log by 1 over the expression inside the log times the derivative of what's on the inside up there. This is over 1. So this is going to be 12 over, this is limit as x goes to 0. 12 over 1 plus 0 is 12 over 1 is 12. So ln of y is 12, and y is equal to e to the 12th. That makes the limit as x goes to 0, 1 plus 4x to the 3 over x is equal to e to the 12th power. We're going to do this one next. And so this one here, when I plug in, let's look at the graph of tangent. It's going to go to infinity when I come at pi over 2 from the left. And the graph of cosine goes towards 0 as I come at pi over 2 from the left. So this is infinity to the 0 indeterminate form. So y equals this limit as x approaches pi over 2 from the left of tan x raised to the cosine x ln y equals limit as x approaches pi over 2 from the left of ln of tan x raised to the cosine x ln y is equal to limit as x goes to pi over 2 from the left cosine x times ln of tan x, like that. And so this is going to be ln y is equal to, let's just evaluate this. This is going towards 0, and then this is ln of infinity is infinity, so this is still 0 times infinity. I need to get this one down, so this is going to be limit as x goes to pi over 2 from the left. Bring this down as a secant, ln of tan x like so. And now this is going towards infinity over infinity. If I look at the graph of secant, I come up pi over 2 from the left, it's going towards positive infinity. So ln of y is equal to, by L'Hopital's rule, limit as x goes to pi over 2 from the left. And then this ln here, we'll get the reciprocal of this, so that's going to be cotangent of x times the derivative of what's inside is going to be secant squared x, and then this is going to be secant x tangent x down here. One of the secants will cancel, and I'm going to just rewrite everything in terms of sine and cosine. So ln of y is equal to, this is going to be cotangent squared. So this is cosine squared over sine squared times 1 over cosine. One of the cosines will go away. And this is limit as x approaches pi over 2 from the left. So I have a cosine left there in the top. So that's going to continue to go to 0. This is 0 times 1, and this is 1 times 1. This is going to go to 0. So ln of y is equal to 0. Y is equal to e to the 0 is 1. Let's see, I have another example here. I don't know that I have. I'm going to come up here to work it on this blank page right here. So limit as x approaches pi over 2 from the left of 13 tan x minus 13 secant x is going to be an infinity minus infinity indeterminate form. Can't use L'Hopital's rule yet, so I'm going to rewrite limit as x goes to pi over 2 from the left. I'm going to write this as, I'm going to pull this 13 out front because that's really not helpful. And I want tangent as sine over cosine minus 1 over cosine, like this. And then 13 limit as x goes to pi over 2 from the left of this is going to 0 over 0 now. If I combine these, which is an indeterminate form where I can use L'Hopital's rule. 13 L'Hopital's rule, limit as x goes to pi over 2 from the left of cosine of x over negative sine of x. And that is going to 0 over negative 1 is going to be 0. And so the limit as x approaches pi over 2 from the left of 13 tan x minus 13 secant x is going to be 0. All right, that's it for this video. And that kind of, oh no, I've got another one. My apologies. Let's say L, which is this limit, is limit as x approaches 0 from the right of sine x to the x, which is going to go to 0 to the 0. I'm going to make this y equals, and then ln of y is equal to limit as x goes to 0 from the right of ln of sine x to the x is going to be ln of y is equal to limit as x goes to 0 from the right of x ln of sine x. Ln of 0 is going to negative infinity. And this is going close to 0, so I'm going to rewrite this as limit as x goes to 0 from the right. This is going to go to a 1 over x down here, ln of sine x up here. So ln of y is equal to, and this is by L'Hopital's rule, since this is going to 0, infinity over infinity now, that's an indeterminate form. This is negative infinity over positive infinity, but I can use L'Hopital's rule now. So this is going to be limit as x approaches 0 from the right. The reciprocal of sine is going to be cosecant, and nothing inside the sine function that I need to take the derivative of, minus 1 over x squared. Let's see, times, so u is sine, so I have 1 over u times du dx, so I need a cosine here as well. So this is going to be equal to limit as x approaches 0 from the right, a negative x squared cosine x over sine of x. And that's still going to 0 over 0, which is an indeterminate form. And then I'm going to have to apply L'Hopital's rule again. And I am going to have a product rule in the top, so derivative of the first piece times the second plus derivative of the second piece times the first. This is limit as x goes to 0 from the right. So this is going to be approaching 0 times 1 plus 0 times 0 over 1. It's going to go to 0. And don't forget that this is ln of y equals 0. So y, which is my limit, is equal to e to the 0, which is 1. All right, that is my final problem for this video now. We'll come back next time and we'll start talking about antiderivatives. As I said before, this wraps up our discussion of limits, continuity, derivatives, and so on, which is our first big topic in calculus. Now we're going to move on to the beginning of antiderivatives, which is also called integration. So we'll start that topic next time. See you for the next video.